Hello YouTube, welcome back to my channel. My name is Tony and today we're going to continue our journey to dynamic programming. And in the previous videos, we already discussed knapsack, minimax, and intervals, and today we're going to talk about double sequences, which is one of the simplest type of dynamic programming. And just like always, we summarized a whole bunch of problems, and if you understand all of them, you'll get the core idea for double sequences. And there are actually two types of double sequences problems, and one type is we are given two words or two strings and we're trying to match them up by either making some operations like deletion, insertion, or modification, or we are given like three sequences. We are trying to manipulate with two of the sequences and to match the third sequence, and that's the second type. So without further ado, let's go ahead and check some concrete example, and that's the type 1 problem. So let's read the question. Delete operations for two string. Given two words, word 1 and word 2, find the minimum number of steps required to make word 1 and word 2 the same, where in each step you can delete one character in either string. And so example number 1, we are given two strings and we're trying to match them up by have the minimum operations. So what are the operation we can do, which is by deletion, delete one of the character in either string. So which means we can delete the string in the word 1 or the word 2. So how do we think about this problem? So like always, if you check my previous video, you realize I actually prefer to use top down instead of bottom up, and you will see why in one of the example, because one of the example we're going to track the previous character, which bring up the dimension to third dimension if you're using bottom up. But when you use recursive approach, which is by using DFS with the memo, and all we do is add one more parameter and track that particular parameter, which is much simpler in terms of the coding, and we will see like when we reach that slide. So how do we think about this particular problem? So we are given two string and ASCII, EAT. So how do we match them up? By making deletion. So here's the example right here. So we can delete S from the first string and we can delete E from the second string, and the rest of the string EA will match the right hand side, which is EA. They are actually matching up. But how do we think in terms of a computer? If we check the example really carefully, and we can tell that EA is equal to this EA, but how do we match them up? And it's actually by shifting. So how do we do that? So S and E are different, and in terms of the two strings, when they have one particular characters are different, so we can shift them up. So let's check the details, right? So we have I index right here under the C and another index J under the it, and I and J are not equal. So in terms of this, so we can either making the deletion for string 1 or string 2, but which one should we pick? Because we are using dynamic programming and we are using top down, so we can break down the bigger problem into smaller problem. So we're gonna try both operation, make the decision as a decision tree. So I'm gonna remove the first character from the left hand side, so which I'm incrementing my I all the way to I plus 1. So now I'm comparing EA with EAT. That's the first option. Now like I'm putting my I back and J is still right here, and now I want to compare EA with the SEA. So what I do, AT with the SEA by increment my J. So my J is under A right now, so the rest of the string is going to be AT and compare with the SEA. But as a human, you will realize this is not the best option, and when we increment I, so that's going to be the option for the eventual global optimum. But the computer does not know that. So as a computer, the computer will try both options and try all the combinations and trying to give the eventual results. But so if, okay, so the given condition is 500, right? The length of the word. So which means that when you're using exponential approach, and that's going to be 2 to the nth power, that's not going to pass the case. But how do we optimize it? So there's a way to optimize it, but think about it. So when we using the recursive approach, and a lot of the cases are kind of repetitive. For example, you have a really long string in the first on the top, and you have a long string in the bottom. So you trying to delete the first character on the top and delete second character on the top, and the bottom, and then you're comparing with the and then you delete one of the character in the bottom. So now you already delete two character on the top and one character in the bottom. In the sequence of delete top, and bottom. But what if like you have the recursive call with the different orders? You delete one on the top, you delete one in the bottom, and then you delete another one on the top. So you're comparing exact the same substring from the top to the bottom, but you are computing this twice. So we see the decision tree just like the Fibonacci when you first encounter dynamic programming with the top-down. A lot of the recomputation for the substring. In that case, we can use I and J to represent the state of each unique computation for the subproblem, and we cache the value, and then we bring back the value when we actually need it, and that's how we solve that. So let's check the code and get some concrete feeling about our example. So this is the Python code, and I know this is confusing for Java and C++ developer. So in the next slide, we're gonna manually cache that. But right now, I'm using the manual cache, the decorator cache from the Python trick, but this may not be recognizable, so let's ignore that. Let's treat this solution as a recursive approach, and let's see how we do that. And then we have 2 0 being passed in. One is I and one is J. That represents where we start. So on the top string, where we start with I, index I, which is 0, and J will start from the second string, which also start from index 0. And let's ignore the base case. Let's come back to this and go over the recursive function we have discussed. So when we have two strings are different, when S, E are different, so we are shifting S, or we're shifting the T. So we are shifting the first character, first the sequence, and we are shifting the second sequence. How do we do that? So just like what we described, we increment I, which means that we are removing this guy. We are delete this particular S, and we are trying to match the rest of the string to the bottom string. So we are comparing EAT to EAT. Okay, so we're comparing this guy to this guy by increment I. But when we delete this particular character, we did one operation, and the question is asking, what's the minimum operation? Find the minimum number of steps, minimum operations required to make them equal. So the operation cost is 1, but this can be vary in different problem. In this particular problem, each step is 1. That's why we're plus 1 right here. It could be different, and you will see that's the only difference for the rest of some of the problem. So we are plus 1 for one particular step, and this is the cost for that step. Or I don't want to delete the S. I want to delete this E and comparing the ATE and blah, 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 all the way down and to this guy. How do we do that? We increment J from here to here, and we still comparing with the I. And then we are shifting the J, shifting the word to the previous version right here. We are shifting the word 1. And in this problem, I'm shifting the J. So once I have the both option, and then I want to get the smaller one because I'm trying to minimize the operation cost. Each cost is 1. And by using the recursive function, I'm not going to solve that. So that's the condition when we have two substring are different, when the current characters are different, we are shifting around. But what about when they are equal? For example, we are checking this substring, E all the way to T and E all the way to T. E and E are identical, so they are the same. Do I need to remove any one of them? I do not. So all I need to do is increment I, increment J, they move forward and they move forward without any cost. I don't need any cost because they are just simply move forward without deleting. They could be equal. That's what I'm doing right here. So with the understanding for the recursive function, now let's think about the base case. So when the game will end, when we'll finish the entire problem, is when I and J, they both reach the, I'm sorry, this is supposed to be N actually, not M. When they both reach the end, that means they already matched. Oh, they are not matching, like they have so many different characters. but we already incorporated all the cost in the recursive function, so we don't care anymore because we already accumulate all the cost. So by the time they reach the end, they are done. The game is over. We already accumulated all the cost, and that's where we found the match. But is there any way we cannot find a match? Yes, there is. So for example, the first string is ASCII, the second string is super damn long. And by the time I is finished and J is still up to here, so what do? So you already matched this guy to the subsequence for all the way to here, and you are still left over a lot of the characters. So what we do is we remove all of those. But how do we remove all of those? Each time we can remove one of them. So we have to remove these 4 times. How do we calculate that? We know the J index is right here. That's where we traverse up to, and this is the entire length of the entire second word. We use the entire length, subtract the J, and that's how we get how many deletions we need to match the first word. The same example happens when we have longer word 1 and shorter word 2. So we match EAT to EAT all the way to, in this case we actually perfectly matched. But what if like we match all the way to here and I is here and J is already finished? When I is here and J is finished, we need to use the length for word 1, subtract the index I to get how many removal we still need. And that's the 2 cases. So when we consider the both cases, we can write one, but this is really bad example for Python. So it's better to write different conditions. For example, when I equal to m and return n minus j. When j equal to n, we use return n minus 1. That'll be a better understanding for understand this problem. But I compact them together in 2 lines, but that's not good. Anyways, with the understanding for this base case and this base cases, we are solved this problem. The only problem we left is the previous discussion we had when this is exponential. How do we cache that? In Python, inner function, you can just doing this as a trick. So this function will use I and j as the key to cache all the values. When you return a value, the value will be cached for this particular parameter as the key. So when you recalculating this, so you will just bring back from the cache, but that's not the other developer will use. So we have a generic way to do that. That's in the next slide. So we can use a hash map, and we pass the hash map to the function, and whenever the value and the unique key represents the state was being calculated, we just bring back from the cache. Otherwise, we store the smaller problem into the cache, and that's how we do that. And along with the other base case and recursive function does not change, they all remain the same when we do the manual cache. The only thing changed is the cache parameter we passed and how we store that. And very simple step, we always start with recursive function and modify this to the cache version. But sometimes, like when you're doing the contest, you want to save some time, just go ahead to use the recursive with a little trick. But I do recommend to start with this to understand how we cache that, and then you can slowly move on to using the simple code. Okay, perfect. So now we understand the first problem, which is the super basic one. And now let's check the second one, minimum ASCII deletion for sum of 2 strings. Now we are given the exactly same example, but let's check the problem. Given 2 strings S1 and S2, find the lowest ASCII sum of deleted characters to make the 2 string equal. So we still want to make them equal by using deletion. The only thing changed is the cost. So I don't actually, before I show you the code, let's go back to the previous code, and we actually can modify it on top of here. So all we want to do is making the 2 string equal, so still the same, right? So when 2 string are not equal, we can shift I, or you can shift the J, compare the rest of them. We twist them from upper side or the lower side. We can shift S, we can remove S and become E all the way to T, compared with the entire string in the bottom, or we can cut right here. So we can remove E from A to T compared with S to T. But now the cost is different. The cost used to be 1, but now the cost is the ASCII value. So all we need to do is remove this guy and replace that with the ASCII value. By Python is the order, and you put the parameter right here. Perfect. So, and there's another thing is being changed. When m minus I represents like when we have i's reach the end, j's reach the end. For example, j is pretty short. I have not. I is in the middle of somewhere. I is here, and we're gonna use the entire length minus right here. But we wanna take the accumulation not for the character length, but we're gonna take the accumulation for the order. We're gonna take the ASCII value for each of the character, and that's what we're doing. So that's the code will look like. So everything else will be identical, and when they are the same, they both shift into a forward. When they are different, so we shift the upper one, shift the bottom one, and all we do is plus the ASCII value for that one. And then when they are different, so we take the summation for their ASCII value, and that's what we're doing. Okay, perfect. So we solved the last one by using exactly same code with the problem one. It's just as simple as that. So let's think about another similar or identical problem. So it's different problem, but it's amazing. You'll be amazed like how the solution for this will be shocking, utterly shocking. So given a string S, in one step you can insert any character at any index of the string. So now it's not deletion anymore. So you can insert. And there's another slight difference. And this problem want to find a string, and you want to make the string as a palindrome. So there's only one string is given. Okay, perfect. So we are given a string, and this time it's a slightly different actually. So we are given a string. So we want to see if this string is a palindrome or not. So we want to make the insertion to make this a palindrome. How do we do that? So now we still need to index, because when we want to make a string a palindrome, we want to check if we fold from left to right between the middle, they will be identical. Can we do that? Yes. So now we still need to index from left hand side or from the right hand side, and we still have two cases. When they are equal, perfect. So we can move the index to the right, move the index to the left. So now like they're from the both sides, and they're moving toward the middle. So that's the cases when they are equal. But what about they are different? So O is right here, E is right here. So in this case, we can also shift. So we can increment I by checking if this guy can form a palindrome or not, by ignore the L. But wait a minute. So isn't ignored L is like deletion? Yes, but we can also think like this. So when we shrinking, like when we increment the I to I plus 1, when we compare E to E, we can treat one operation like this. So we can add a L right here. Removing L cost 1. Adding L on the right hand side is also cost 1. They are identical. So that means when we doing the insertion, it's the same thing with the removal, because when you add something on the right hand side, it's the same thing to move something on the left hand side. That's the key idea when we're doing the double sequences, because we can translate one problem to another problem, even though they have different operation, but we can envision them into the same identical problem. So we can shift I to the right and check the subproblem like here. We can ignore L by pretending we are adding L right here. That costs one operation. Or we can compare all the way from lead all the way to D, and we can ignore the E. that's removal. But when we actually doing the insertion, we can also add E to the left. So then we can also ignore this guy anymore because we already matched them up by insert AE on the left hand side. Now we are still left LEETCOD. So that's when we shift to the right or shift to the left. Okay, so once we have these two operations, now we realize this problem is almost identical to the previous one, except that we start from the both side. And now let's check the problem, how it works. So we still have the 0 and -1. So now the index is different right now. The index start from left, the index from right. I is here, J is here. When they are different, we can check the substring from E to T or the substring from S to A. So E to T will be I increment 1, which is this guy. S to A will be J minus 1, will be this guy. And the operation cost 1 because I'm trying to, when I compare E all the way to A, when I'm removing T, that means I insert a T right here. The insert cost 1 operation, and that's how we do it. And now we can even make, before we do that, right? So that's when they are different. But what if when they are the same? For example, A, and this guy. When A and A are identical, so we can increment I to here, decrement J to here. Now they are the same. So we don't need any cost. That's why my I will going forward and J will be minus. And when they are meet in the middle, when I and J are equal, that means we don't need any cost anymore because they are already met. They're already met. And now we have a palindrome. All the cost will be increment right here. This is incorporating all the cost. And eventually we cache the I and J. So I'm not sure you have. Oh, I don't have the manual cache version, but you get the idea. So you can add a cache, and just like what we did in the previous slides. But now we got a key idea for the recursion and the base case and the cost. Now we can even make a problem. So we can say, hey, what if the cost cost like ASCII, and how do you do that? So you can actually do it right here. All you do is like change this particular one to a ASCII order, right? So you ASCII value, and you can even make the problem yourself. And that's the core idea for this. Okay, let's move on. Oh geez, this is the classic dynamic programming problem, longest common subsequence. This is so classic. You learned this in the textbook. I'm not sure like why LeetCode putting this as a 1,000 plus problem, but this is so classic. And we are given two common substring, and text 1 and text 2 return the length of the longest common substring. Subsequence. A subsequence is a string, a new string generated from the original string with the sum of the characters can be none, deleted without changing the relative order of the remaining character. ASCII is a subsequence of the A, B, C, D, E. Because we have ACE, we can skip the characters. And the AEC, by the way, substring and subarray are so totally different story. Subsequence, we can skip the characters, but subarray cannot. So that's why a lot of the subarray problem can be solved by sliding window, which we will talk about in the future videos. But now we are talking about DP because subsequence mostly solved by DP or backtrack or stuff like that. Okay, a common subsequence of the two string is a subsequence that is common to the both string. We have A, B, C, D, E, and we have ACE. Now we can pick A and pick C. We can pick E, and now we can find them. A, B, C, D, E, ACE. So we can pick A and C as E as the subsequence and then match them up. So that's the longest common subsequence they have. And ABC, they only have 3 letters, and they can only be have like 3 letters identical. Okay, so skip the examples, right? Let's think about this problem and what are the options we have. So when we check, still like we have 2 different index, right? We have I index right here and J index right here, and we're trying to compare them. If they are equal, whenever they're equal, right? We found a match. So what do? We increment I, we increment J because we know they're identical. We found one. And we are not calculating cost. We are calculating the longest common subsequence. So when they are equal, we increment the count by 1 because we found one match. So A and A will be identical, and B and C are not. So we'll start doing the shifting and stuff like that. But when we do the shifting, they are not incrementing the common subsequence because we didn't find one. So that's why we're doing the shifting without any accumulation for the values. So we have B, C, D, E, we have C, E. So we shift the left first. So we shift I, incremented by 1. So we have C, D, E compared with the C, E. Okay, perfect. So that's going to be another recursive function. And then we can shift the J, we compare E to the B, C, D, E, and that's another recursive function. And we find the maximum between these two. But do we have any increment? Like we mentioned, nope, because we didn't find one common character. So that's how we solve the problem. So we calculate the length for S1 and S2, and then we start from the beginning, I and J. So when we found one match, we add them up. So when they are equal, we match them up. So we increment both I and J with 1, and we also increment the count for the common subsequence because we found one character are identical. Otherwise, we shifting, and for example, we compare B, C, D, E with the C, E. We shifting B, we have C, D, E. That's where I will be increment. I will be increment. Otherwise, we compare B, C, D, E, C, D, E with the C, D, E with the C, E. So J does not change, and I change. Or we change J, I does not change. So we find the maximum of them. The recursive function will find us the maximum value. How? By the base case. So we already accumulating all the values right here. So we need to stop in the base case. How? If one index reach the end, that means we cannot find more common subsequence anymore because we used all the values for one of the string. Same thing with the other index. If we reach the end, we already use all the characters within the string. So we are done. And we return 0 because we cannot find a more common subsequence anymore. And that's how we solve it. And we are adjourned with this particular problem. Okay, perfect. So with the understanding for this, and let's move on to the next one. Oh, I'm sorry. Before we move on, so I put a menu cache. So we can ignore this because they are identical, putting the memo right here, and then once we calculating the smaller problem, so we bring back from cache. Otherwise, we store that. So which is identical and nothing new. So move on to the next one. Added distance. So this problem is a slightly more difficult, and I remember that when I read cracking coding interview several years ago, that's one of the classic one, and you can tell that there are a whole bunch of variations on the lead code for the same type of problems. So let's read the question. Given two strings, word 1 and word 2, return the minimum number of the operations required to convert word 1 to word 2. And you have following 3 operations permitted on a word: insert a character, delete a character, replace or character. So still, we have 2 options, right? When 2 characters are the same or not. So we still start with I and J in the beginning of the index. So when they're the same, do we need to do any option or operations? Nope. So we just move forward. I++ and J++, and we don't have to concern about anything. But whenever they're different, we need to think about 3 things. Which operation should we make? In this case, we have 3, and it used to be 2, right? Either remove or something like insert, and now we have 3. Why don't we just try everything out? So how do we try them out? So we have 3. Which one is the easiest one? So I feel like replace will be the easiest one because H and R are different. So I would replace H to R. If I replace H to R, this particular characters are already the same, and I'm gonna increment I to O, J to O. Okay, so now we matched the first character by 1 cost. What is the cost? Replace. So that's the 3rd options we have when we have different characters. Or we have insert and delete. But how do we do that? Now let's think about it. if I remove this guy, the H is being removed, and I'm trying to match the rest of the substring to ROS, my I will be incremented because I'm trying to compare the rest of the string to this guy. So that's why my I will be incremented. Perfect. Or I can do what? I can do insert. So if I insert something, what would that be? I'm comparing with R, and I'm gonna insert R right here. If I insert R, my I will still be here because I'm still haven't matched them yet. All I did is insert something right here. My R already being matched. My J will be increment. So which means when I do the deletion, my I will be increment. When I do the insertion, my J will be increment. Or when I do replacement, both will be increment. All of them cost one step. That's what I'm doing. So when I and J start from 0, when they are equal, they both increment with 0 cost. Or I can increment, I can do deletion by removing this guy. Well, my I will be increment. Or I can do insertion, insert A right here to match this guy, and my I will not be changed. My J, this is already being matched by the inserted character, and my J will be changed. All the options, I'm picking the smallest one with one operation cost. That's what I'm doing here. And cache the value, and then we'll get the results. And same thing when I reach the end, and we still have us left over for another string, and then we use the length to minus where J is up to. Same thing for J. When J reach the end, and we subtract the where I traverse up to, and that's the base case like before. And I'm not gonna beat the dead horse, and same thing, I'm not gonna beat the dead horse for this as well. We cache the value, and then we have the recursive function. Perfect. So let's move on to next one. This is the second type that we are talking about in the beginning of the video. We are given 3 substring or string, and we are trying to match 2 of them to the third one. And this graph might be intimidating, but what we did is we have I here, we have J here, we have K here. Each time we are popping out a character from this string. We are trying to match with one of them. Does A match with one of them? Yes, we are matching with A. Does this A match with A? Yes, it does. Does this D match with any of B or D? It does. Like when we keep going forward and we match with every one of them, and then we return true because these 2 subsequence can form the third subsequence, and that's what we're doing. And by reading the question, so we can realize that in this problem we will need 3 index I, index J, and index K. Whenever this guy match one of the I and J, we can move forward. Otherwise we shift, and that's how we're doing. Perfect. So here we go. Oh, by the way, we're not shifting because we are checking true and false, right? So if, for example, there's an E right here, but none of them has E, okay, we failed. That's why we just return false. Okay, now we can go into the code. Now this time, like in terms of the inner function, we actually don't have to pass like S1, S2, S3. This looks confusing, but just ignore this 3 parameter and just imagine that we're gonna have this particular 3 index. I and J and K start from here and here and here. So let's check the base case first this time. When I and J reach the end and K also reach the end, that means like I, J, K exactly matched what we want, and we return true. Otherwise, when I or J reach the end, K also reach the end, but only one of the I and J reach the end. But which means we still have, for example, C left, and A, B, C, and this guy already matched this guy. We have this guy left. When you're adding this guy to the substring, oh my god! So we have one more character. So that's not good. That's really, really bad, and we're gonna return false. That's the base case. So now, with understanding for base case, and let's going back to the logic that we have discussed. We got 3 conditions. The first condition is is right here, B. This B will match this B will match this B. In that case, should I increment I or increment J? The solution is we try everything. Let's match I first, I increment and K increment, I increment, K increment, or we try this guy, J increment, K increment. We try both. If any of one of the options will work, this will work. Same thing like right here. So if only one of them actually match my third subsequence, that's perfect. Let's go in with that. If the first one match the third one, perfect. First one go, third one go. Second one match the third one, second one go, third one go. Perfect. And that's how we do the manual cache. And okay, so 115 distinct subsequence will be slightly different. So let's read the question. Given two strings S and T, return the number of the distinct subsequence of S and T, S which equals T. A string subsequence is a new string formed from the original string by deleting some, can be none of the characters without distributing or disturbing the relative positions of the remaining characters. ACE is the subsequence of ABCDE, while ACE is not. AEC is not, because the order changed. The AEC is not the subsequence that we already know. Let's check the example. So we have rabbit. Okay, so there are 3B right here, 2B right here. The rest of the character will be identical. R and A, we can just move forward, except B right here. So we match the first B. And now the second B is also the same. And we will have 3 different options. We can use the first B and the second B, or we can use the second B or third B, or we can use the first B and the third B. Now this is a problem. We are trying to match the T to S by picking some of the characters, but the question is guarantee you have the answer. So don't worry about there's a W right here that does not match anything. Don't worry about it. The question guarantees there's an answer. When the problem is already guaranteed, so we can just go ahead and check when they're the same. We'll have 2 different options. So let's think about index I from the left hand side first. Because we are trying to pick some of the character from here to match this guy. So this guy will always going forward. Because for example, my I is here, my J is here. My I will going forward. Or my J will, you know what? I don't want to match with the first B. I want to match with the second B. That's okay. So my J can stay the same when they're the same. That's the thing. So I can move my J, or I can make my J stay the same place to match the second one. For example, my I is here, my J is here. I could use my first I, match my first J. That's okay. My second, and then my I will increment to the second B, and my J will be the second B as well. And this J was like, I don't like this B. You know, this guy, I will increment to this guy, and the third B. And the second B will be like, yeah, I like this guy. So that's how he picked the first one, the third one, which is the third one, third example. So we give the J some variation. This J have the ability to pick which B he likes. And that's how we solve the problem. So when I and J are equal, my I will still be increment, but my J has the priority to pick which B he likes or she likes. And that's how we solve it. So when they are equal, we have this option. But when they are not equal, we have to increment S, because S is the one we are picking from. So if this guy does not match, this is a bad example, but if this guy does not match any of the characters, so we increment this guy to find a character to match this guy, because the question indicating that we guarantee to find an answer, and that's how we solve it. Perfect. So with this question in mind, oh, by the way, so let's check the base case, right? So this is the S, I, and this is the J. When J is reaching the boundary, when we don't have J anymore, by the way, this solution is actually going backward. So we reduce the numbers. So like most of the problem, I used m and n, I initialize the size, and then I pass 0 when they reach the size. But now they are decrementing the length, but it's the same. So when j reached the end, that means, hey, we found a subsequence in S to form a T. Perfect. So that's why we return 1. Otherwise, we exhausted search in S, but we still cannot form a T. We return 0. Uncrossed lines. So we are writing integers a and b in order they are given on the two separate horizontal lines. Now we may draw connecting lines, a straight line connecting two numbers ai and bj, such that ai and equal to bj. That's the first condition. They have to be the same, and the line we draw does not intersect any other connecting and non-horizontal lines. So when we draw a horizontal line, so they cannot be across each other. So for example, right here and here, so they cannot have a horizontal line being crossed. So if I match 2 and 2, they'll be crossed. And return the maximum number connecting the lines we can draw in this way. So without crossing, right? How many lines we can draw? It looks hard. It looks like a graph matching problem, but can we translate to something we know? But actually there is, right? So all we need to do is find the maximum common subsequence, because whenever they have the common subsequence, they are not crossing, if you think about it carefully, right? And I'm not even gonna be the dead horse. And when they are identical, so we increment 1 because they have the common. Otherwise, we're shifting 1 on the top, we're shifting 1 in the bottom. So they are identical code. So if you copy and paste the code from the longest common subsequence, and it will pass this case. Oh, perfect. So shortest common subsequence. In this case, we are finding something different. We are giving string 1 and string 2. We are trying to find a string that interleaving a and b. So what does that mean? So remember the question, interleaving string. So we are trying to see if the first string plus the second string, if they are doing the crossing, and we increment I and j if we can match the k, and that's the problem. But now the third sequence was not given, and we are gonna find it. And so there are two ways to solve it. One's using top down, and one's using bottom up. And this is one of the questions that bottom up will pass the test, but top down will not. So this is one of the rare questions, but I still provide the top down approach. So when they are the same, so they both can be increment because we find a match. So for example, ABA, AB, so AB could be the common, right? AB could be common, but C is not. So that's why we need the C right here. So when they are different, so we need to check. We either add C, for example, A and C, right? We either add C in the front, or we either put A in the front. We try both way. So whoever has the smallest final string, super string, we got them. We got it. Okay, so that's how we do it. But in this problem, so we're gonna use top down. So same approach when they are equal. So I'm not sure, like I actually didn't explain the bottom up approach, but this actually represents the previous steps. So when I decrease 1 and j decrease 1, that was the previous condition. So they plus 1. That's the same thing with right here. But we're building up from smaller problem to bigger problem. But this one is breaking down the bigger one to smaller one, and it's slightly different, but it's more like the opposite. And we do the shifting, and then by this way we build a matrix. The matrix will be representing that the smallest superstring, and for the matrix, and based on the matrix we can build that. So you can read the code and trying to like debug, run it in the debug mode. So because I didn't cover the basic, it will be really hard to go into the details. So I might just make a separate video for the bottom up for this approach. And by using the graph, I think it's easier to understand that. But just by talking, I feel like this is really tough. But the top down approach will be perfect. This code will be better understanding. But unfortunately, this code would not pass. It will be like time exceed limit. So that's one of the rare problem, like we mentioned. Okay, let's move on to next one. So I might just come back to this like in the future videos to talk about it. The valid palindrome. So now the problem asks us, given a string and the integer k, find out if the given string is a k palindrome or not. So what is k palindrome? A string is k palindrome if it can be transformed into a palindrome by removing add k characters. Oh, this is getting harder. Okay, the restriction is k. K is the restriction. But do we care about it? We're just gonna use dp to find out the minimum removal, right? And then we compare with the 2. If it's smaller than the k or not, right? Okay, perfect. Let's solve in the traditional way. So when I and this I and I are same, so we don't have to remove anything. Otherwise, we shift around. So same thing. So when they're equal, so we shrink. Otherwise, we shifting. And then we compare the final results with the k. If it's less than or equal to k, perfect. We find a match. Okay, so that's actually translated to something we know, except the k. So we put the k in the last and compare with the final results. Okay, let's try something like really fun. Dot products. So what is dot products? It's like a tongue twister. Dot product. So we have a 2 array. They has to be identical. They have the length for both array has to be identical. But the problem saying that is 2 subsequence. So for example, we have 2, 1, -1, -2, 5. So we're gonna pick 3 number from here. We're gonna pick three number from here. So we multiply each element respectively to find the maximum number. This looks really hard, but we can break this down into something we know, which is double sequences. Because we have 2 sequences, right? 2 subsequences. We are picking some exact number to match this and to make the maximum value, with a slight caveat. And what is the caveat? The caveat is we have the negative number right here. So which means we could abandon whatever we already had, still get the maximum value. If you collect the value from this guy, right? Let's say here. So if you have -2 times 2 is -4, that detriment your final value. It actually lower your final results. You don't care about this guy. So that's why I'm not even need this guy. So you can restart from beginning. That's the core for this problem. That's the only difference that makes this problem is different from other one. And another caveat is, it used to be the operation cost is, or reward is going to be 1. But in this case, we have nums I times nums j, and that's the reward. And that's the only 2 things we have to care about. And now we can go back to the problem and think about how we match that. We have 2 options. We can either increment I or increment j, or we can abandon everything. And that's all the options we have. And now we can check the code. Okay, pretty short, but not so obvious. We pass 0 and 0 in this. And then we, let me add example at the top. Just give me a moment. Super simple example, but I think it's gonna demonstrate what I'm talking about. So we have I right here under 1, we have j under -1, and so what we can do is I'm gonna pick these 2 numbers, I times j, which is -1 as my current value. So I increment my current value in this operation, and then I increment I and j because I already picked this number. Perfect. Okay, so I already used up this number. I cannot reuse that anymore. So I plus and j plus plus. Or I can do this. I don't like this guy. For example, this guy has 5 values and this guy has 3 values. So I'm gonna skip this guy. I'm gonna use my precious little values to match. This guy has more weight. So for example, you have like three guys right here, 5 girls right here, or three girls right here, 5 guys right here. This guy always, or this girl always has more ways to pick because the quantity is different. Okay, and this person will pick, has more options to pick, and that's what I'm talking about. So that's why we're shifting this, or like we can have more ways, but we're gonna try both way. Everybody has their right to be a picker or not. So that's why we shift either I or J. Okay, so this is another two options. Or would we first initially pick this guy, right? I increment and J increment. Now I's here and J's right here. And they'll realize, wait a minute, this guy is a douchebag. And this is -1. We don't want this guy. Because this detriments our total value. We want to abandon this guy. And can we abandon this guy? Yes. All we need to do is pick the current value. Forget about the rest of the value. Forget about the rest value. And then we take the rest of them. And that's how we pick the maximum number. Okay, now we got this problem. Whoa, wait, this is the last problem. Okay, I think this is a good catch or summary for double sequences. In general, this topic is pretty simple. I couldn't find any hard problem for this, even though some are labeled as hard, but I highly doubt it. And there's only one problem, cannot be solved by top down, because top down will have the TLE. But the rest of the problem will be super simple, and there are only logic you have to think about. Either they're matched or they're not. So when you match, which one do you increment? And that's all you have to think about. And if you liked my video, then please subscribe to my channel, and I'll see you in the next video.